What is it? Oh, Boston cream. Okay, people are trickling back in. All right, I think everybody should be back here. Okay, I took a picture of the breakout rooms. Breakout room number 1, Ashley P, Daniel, John, and Joshua. What do you got? Who is your designation for person to share? What do you got?
The same. So we came up with 2 methods. The first one was early in the semester, we were talking about the mixing of the paint can method. So basically do something similar to that, so that way, in this case, you would know the key beforehand and then just work out which person gets what. But that would be the one method. The other method would be something where like each person is given a prime, kind of like P and Q, multiply together to get M, and you would not be able to figure out M with just P or with just Q.
Cool. Okay, good. Sorry, my picture went away on my phone. Let's see. Ashley, Sheriff, Laura, Lucas, and Mandy. What do you guys got?
Yeah, we kind of talked about like if your key is some number, then dividing it among the people so that you have to add up everyone's individual numbers to get the final key, or like multiplying them or something like that.
Yep. Okay, cool. Cody, Elijah, and Jenna.
We kind of thought about the paint bucket example too, so kind of like using the Shamir 3 pass, but doing it with more passes, kind of. And then I also personally thought about how the protocol that I looked at could be extended, for my paper, could be extended to more than 2 people for the quantum cryptography.
Yes, and extending this to beyond 2 people is definitely a challenge. The last one, Jason, Sarah, and Seth. What do we have from you guys?
We talked about the mixing of paint, but then we also were like, once you mix the paint, then they would both know the key.
Right. And that's okay. So, and the paint mixing thing, definitely, it's okay that once everybody comes back together that they know the key. That's fine. It's just that we need to make sure that you don't know the key if you have just your piece of information. So when everybody's piece of information is put together, that is fine to know the key. Good, spectacular. Thank you for playing discussion in breakout rooms. I know it's not entirely natural. So here's one way to do it. We talked about a bunch. All of these are good and valid. If M is the secret piece of information, you want to split it between Alice and Bob. We're going to pick a random number R, and I think somebody talked about this, and I'm not sure who. So you want to distribute R to Alice and M minus R to Bob. So this is kind of what, maybe it was breakout room number 3, the third one you guys did. You can add them together then to get the secret M, but on your own, neither person has it. And they can reconstruct by adding. So the how is a really stupid question at this point in time. Add, obviously. You could do it with multiplication also if you wanted to. So you could divide the key up into division instead of subtraction, and then you could reconstruct the key that way as well. So both of those are possibilities: division, subtraction, etc. Easy? Good? Easy? Notice that this requires what's called a central authority figure. So there's somebody who has to know the key overall and be distributing it. So it's a central authority figure or a key distribution figure. That is a requirement in this type of secret sharing scheme. So you can do this with 3 people also, right? It's going to work with 3 of them. So you just pick 2 random integers. I have them mod n because this is going to lead into the next secret sharing scheme that we're doing, but you wouldn't have to do mod n if you wanted to. So then we distribute r and s, and then our last piece is m minus r minus s. And this would be, again, mod n if you wanted it to lead into our next one, or you could just do it regularly, however you want to do it. And then once again, if Alice, Bob, and Carol all come back together, they can add, they can get the key by combining all their pieces, but none of them know the key, the secret piece of information on their own. And again, the how is obvious. Okay, So secret sharing schemes do not present a ton of challenge. Are we good? Everybody's good? So give me a thumbs up. Secret sharing schemes, easy, no problem, all good? Okay, these are not a big deal. We've known how to do these for quite a while. No problem, easy. You could do it with paint mixing also, easy, no big deal. The interesting part that we want to talk about is the next one, which is called threshold schemes. So this is kind of secret sharing schemes, but with an added twist. And the added twist is maybe I don't want to require everybody to be present to reconstruct the key. So maybe if we're going to split the secret among Alice, Bob, and Carol, but maybe it's unreasonable to assume that all three of them can get together. So we would be okay for security reasons if only two of them came together to reconstruct the key. This is called a threshold scheme because the threshold part is the number of people that you need to reconstruct the key. So in this case, and I'll have the specific notation on the next slide, but in this case, the threshold is 2 because 2 people are required to reconstruct the key. Technically, every secret sharing scheme is a threshold scheme where the threshold is equal to the total number of people. So secret sharing schemes are basically a specific example of threshold schemes. Threshold schemes are more general than secret sharing schemes. It's kind of like, and if you've taken any of my classes before, you've heard this example 800 times, squares and rectangles, right? Every square is a rectangle, not every rectangle is a square. Every secret sharing scheme is a threshold scheme. Not every threshold scheme is a secret sharing scheme. So that's the relationship there. If you ever teach math, I hope that you use the squares and rectangles example because that's my legacy to you. Okay, here's the technical definition. So it is called a T, W threshold scheme. W is the number of people that you are distributing the secret among. So that's what the W is, T, W. And you might see the T and the W reversed, but you'll be able to tell which is which because W is always bigger than T. So even if the numbers are reversed, the bigger one is W, the number of people. And then the T is, again, the threshold, the number of people needed to reconstruct the key. So W is the total number of people involved, the total number of people who are getting shares, and T is the number of people that I need to reconstruct the key. And I want to do this like we had the previous one also. If you get fewer than T people, they can't reconstruct the key. They can't reconstruct the secret by putting all their information together. So those are the 2 requirements for a threshold scheme, or the definition. T people, any T people put together can reconstruct the secret. Fewer than T people can't. That's what's going on here. And again, practical example is not very exciting. President of the US, Chairman of the Joint Chiefs of Staffs, Secretary of Defense, and 2 of them want to be required to launch a military strike. So 3 people total, 2 that are required to launch a military strike. This would be a 2, 3 threshold scheme. Okay, this is harder. And the reason this is harder is because you've got a whole bunch of different combinations of people going on, right? If we have Alice, Bob, Carol, and Dave, and we want to do 2 of them to reconstruct their key, there are 4 choose 2 potential pairs of people. Alice and Bob could come together, Alice and Carol, Alice and Dave, etc. We got to make sure that any of those pairs coming together can reconstruct the secret. That's why this is harder. So there's plenty of secret sharing schemes out there. I am going to talk about one. It is called the Shamir threshold scheme, invented by Addie Shamir in 1979. Shamir threshold scheme. This name should sound familiar to you from RSA, and we've seen his picture already. So this is why I do not have a picture up on this particular slide. So this is the practical example of a threshold scheme that we're going to talk about today. But before we get into that, I've done a bunch of talking, and I feel like I should ask if there are any questions. Anybody have any questions? Do a virtual hand raise or ask me in the chat at this point in time. Anything, questions, comments before we jump into the example of a threshold scheme? Anybody, anything? Okay, so then here's how a Shamir 2,3 threshold scheme works. We can extend this, and I think that that's what we're going to do on Friday. I got to look at my notes for sure. But we're going to start with a basic 2,3 threshold scheme. So again, remember what this means. 3 people total, Alice, Bob, and Carol, are all going to get pieces, and 2 of them put together need to be able to reconstruct the secret. All right, so, oh, I lied. I'm sorry. Alice is our, sorry, I changed my notation. Alice is our secret key distribution authority, and she's going to distribute this among Bob 1, Bob 2, and Bob 3. Sorry, that's my notation. We don't have Alice, Bob, and Carol. We've got Bob 1, Bob 2, and Bob 3. That's who is getting these pieces of information at this time. So she wants to distribute these shares to Bob 1, Bob 2, and Bob 3 so that any can reconstruct K. The reason for this is because I'm going to run out of letters in the alphabet shortly, and so we'll go with Bob 1, Bob 2, Bob 3, and then we could go up to like Bob 16 if we had a bigger threshold scheme. I can't come up with names for that many letters in the alphabet. So here's what we've got. Here's the process. Here's how the Shamir 2,3 threshold scheme works. So remember, Alice is this overarching authority. She knows everything. We're okay with that. You can argue that this might potentially be a breach of information, potential vulnerability in the system, and you can deal with that. But for this, we're going to say, yes, we trust Alice. We are okay with her knowing everything. So what she's going to do is choose a prime P, and then she's going to pick some random numbers, 4 of them. They need to be distinct so that people don't get the same share. So she's going to pick A, R1, R2, and R3. So those are the numbers she's going to pick. She got this prime P. She's going to pick these random numbers, A, R1, R2, and R3. And these numbers need to be in ZP. So remember, that means they have to be between 0 and P minus 1. That's where this prime is coming from. Here's what she's going to compute. 3 S's. So S sub 1, and then the other 2 are going to be the same, just different subscripts. S sub 1 is A times R1 plus K mod P. S sub 1 is A times R1 plus K mod P. That's S1. And then we're going to do S2 and S3 similarly. So S2 is A times R2 plus K mod P. And S3 is A times R3 plus K mod P. Daniel, question?
And that's the whole thing is mod P? Not
Yes,
just
I should put parentheses around the A times R1 plus K. That whole thing is mod P. Yes.
Thanks.
Other questions? Okay, then what she's going to distribute is everybody, all of the Bobs are going to get an ordered pair, R sub I, comma, S sub I. R sub I, comma, S sub I. So that's what each of the Bobs is going to get, R sub I, comma, S sub I. Okay, I want to do a demonstration of this, but I don't really want to type in Perry because that's not going to be particularly helpful. So I'm going to put you back into breakout rooms and have you play with these. Here's the values that I'm going to pick. I'm just randomly picking something here. So let's say that P is equal to 43. There's a prime. Throw out some numbers for me. A, R1, R2, R3. That's a horrible subscript. Either in the comments or just unmute yourself and give me numbers. What do we got? A equals. Somebody give me a number. This is
42.
the interactive part of class. Go ahead.
42.
42. Okay. R1 equals. Somebody else. Give me a number.
5.
11.
I heard 5. I heard 11 for R3. It might have been 7, but I'm going with 11. One more. What do we got? Give me one more number.
19.
19. Cool. Okay. So everybody's got those. P, A, R1, R2, R3. P is 43. A is 42. R1 is 5. R2 is 11. R3 is 19. Breakout rooms. I'm going to put you into breakout rooms. I want you to compute all of these values. So it's going to be the same breakout rooms as before. They are open. Go do that. Take a couple minutes. Go.